Hello everyone, good to see you all here. So as I was introduced that I'm currently an assistant professor at Penn State. I mostly work in networks and system security, particularly the Next-G security and Open RAN security. So I lead the systems and network security lab at Penn State. So today we are going to talk about our latest automated security testing framework for Open RAN implementations. I know that all of us are already very familiar with Open RAN systems, but just a quick recap, that when the mobile networks are transitioning to the 5G networks, there are a diverse set of new applications, services such as Internet of Things, autonomous vehicles like smart factories. Now they are actually being supported by 5G, right? And radio access network or RAN, they help these devices connected to the internet and gets the services. Now with this wide variety of applications and services, there is a requirement for diverse traffic. Now previous generations, they supported monolithic architecture of RAN, whereas the 5G has introduced this disaggregated architecture of RAN, where multiple like single RAN has been decomposed into multiple components, where each component implement portion of the network stack, so that now the RAN operators can sort of get their different components from many different vendors. Now this is not the end of this like a challenge to support diverse traffic. Now RAN needs some kind of network optimization operations because they have to manage it, but to do this kind of network optimizations and control, they need the like a very broad overview of the network. So to address this challenge, Open RAN has been introduced, which decouples RAN hardware from the network optimization versus control. Okay. So and Open RAN actually introduced different types of RAN intelligence controller. One such RAN intelligence controller is called near real time RIC. And near real time RIC, it is connected to the different network RAN interfaces to standardized interfaces, and it collects real time metrics, takes some decisions, the RIC takes some decisions, and then give commands to the network to reconfigure. So as you have seen that with these disaggregated architectures and these kind of capability of optimizations, real time optimizations, it actually promotes the use of different types of hardwares from different vendors, and also it allows the Open RAN allows the RAN to optimize or control the network through softwares, and this software may be coming from either the network operators or from third parties. So let's take a deeper look at this RAN architecture. You can see that at the bottom there are different RAN components, and one Open RAN RIC or non-real time RIC can be connected to multiple RAN or RAN components. So the main interface between the RAN nodes and the Open RAN is the E2 interface. So that through this interface, the RIC or non-real time RIC, they can collect the metrics or data. And one of the main enablers of the network optimization is done by the XApps. XApps are for real time RIC, and RApps are for non-real time RICs. And these XApps are mainly software components running in the cloud as a container, and of course it is written in is written as a software programming language. Now XApps collects the data from the RAN, but to collect the data and make the decision, there are many other intermediate components in that RIC. As you can see that SDL, subscription management, conflict mitigation, and many other internal components, and each of these internal components are actually a software program, a standalone software program written either in C, C++, or Go programming language, and deployed in the cloud as a container. All right. So, as I said, like the real-time metrics are being collected through E2 interface. First, it routes to E2T terminal, and then there are some internal components. The messages are being routed, and finally, it reaches the XApps or RApps, and the XApps and RApps makes the decision, and then gives the control to the RAN nodes. So, everything the thing that you can see on the top, everything is softwareized. Of course, also RU, DU, and CU, many things are now softwareized, as Brendan mentioned in the previous talk, except that we have few hardwares at the very bottom of the physical layer. So, whenever we have software like written in thousands lines of code, of course, there could be bugs, intentional, non-intentional. When you say non-intentional, I mean developers might do some mistakes, because if you write 1 million of lines of code, there should be some kind of mistakes, of course. I mean, we cannot avoid that. Now, there could be also misconfigurations. There could be dependencies in the third-party libraries, like supply chain issues. For many reasons, the software could be buggy. Now, as well as the software running in the RIC or non-real-time RIC could be buggy, there is also hardware and software component in RU, DU, and CU, right? And any of these RU, DU, CU could be compromised by the attacker, and once compromised, they can send malicious traffic to RIC or non-real-time RIC. No, I mean, nonetheless, the traffic that UE sends to the RAN, that UE could be malicious. How? I mean, any UE can purchase the SIM card of AT&T or T-Mobile or any other network operators, and can act as a malicious UE and send malicious traffic to RAN, which forward the traffic to the RIC. So, there are actually tons of attack surfaces in RIC and non-real-time RIC. How can we secure them? Whenever we are we are actually rushing to deploy the Open RAN, but we also need to make sure these RIC, non-real-time RIC, XApps, RApps all are secure before being deployed. So, even the ORAN Alliance, in their specifications, they have mentioned that non-real-time RIC should not accept any malicious inputs. Okay, I mean, every input should be vetted before being processed. So, what can go wrong if inputs are malicious, or even some weird inputs being generated because of weird network operations in the RAN? So, let us assume that at the bottom there are many components, and one component may be compromised, that can trigger some unwanted input that goes through E2T, and that being routed to subscription management, and eventually it goes to XApps, and that malicious input can cause crashes to XApps and subscription management as well as E2T. Now, if E2T, which is the sort of the gateway to XApps and RIC, if that is crashed, then all other RAN components, not only the DU and CU from RAN 1, but also other DU and CU from another RAN can be compromised. I mean, can be get denial of service attacks. Okay, so the communication will be disrupted, and no operation will happen. So, in this project, we are focusing mainly that whether this program crashes or just the program becomes unresponsive, and these issues can be because of out of bounds in your like programs, null pointer dereferencing. We have heard of the CrowdStrike, where there is an issue of null pointer dereferencing, and because of that all the delays in the flights happened. So, these kind of issues may also happen in RIC or non-real-time RIC. So, the hypothesis that we want to test in this work is that can you develop an automated testing framework to check the robustness and operational integrity of ORAN implementations, and we would like to do it before this kind of testing before the components being deployed. So, before we talk about how we designed our automated testing framework, let us first look at the limitations of the existing techniques that industry probably will look for. So, of course, I mean traditional approach is called fuzzing, which is sort of a software testing mechanism. You generate inputs in a smart way so that you can test, but unfortunately none of the fuzzers available in research domain or commercial domain, they are not applicable for testing Open RAN. So, we tested many existing such fuzzers, and they actually poorly failed. So, one such fuzzer is called AFL or version of AFLnet. The idea is that they can only fuzz one program at a time, but as we have seen, the ORAN in RIC, there are more than 10-12 components, they are running in parallel. So, we want to test all of them at the same time, whereas the existing fuzzer can only fuzz or test one program at a time. Now, that is not a bad idea. I mean, you can also do like multiple programs, I mean sequentially with the existing fuzzers. The problem is that many of the interfaces in RIC or non-real time RIC are non-standardized. They are actually like very customized for different vendors. For example, Ericsson RIC would be different from Nokia's RIC, right. So, I mean only the E2T interface is standardized, whereas the internal communications between different components, they are non-standardized. How do you know the message format if you want to test it? So, this approach, the existing approach does not know the message formats, the protocol, whether it is the communication is happening through gRPC or REST API. So, it is very hard to create these test inputs with the existing fuzzers. And if we test one single program at a time without considering the dependencies between different components, there could be many false positives. Means that, I mean it may crash, but actually it may not crash like in an end-to-end manner. By end-to-end manner means that here the attacker might be sitting at the RAN. So, if attacker sends that input, it may not reach to the target program if you test in an isolated way like this. Okay. So, our goal is to create an end-to-end fuzzy, I mean automated testing framework. If we say that we want to test X apps, we will start testing from the E2 interface, so that our test input can reach to the X apps or any other components. Okay. So, this is the basic idea that we would like to do end-to-end testing. But to create this end-to-end testing framework for RIC or non-real time RIC, the first challenge is that whenever you generate inputs from RAN, their inputs have to route through many internal components and finally reach to the target that you want to test. So, these internal components, if your input does not comply with the message format and semantics of the internal components, that internal components will drop your input. It will not reach to the desired target. Okay. So, that means you have to make sure that there are sufficient or proper constraints on the input, so that it can reach to the desired target. If it is under constraint, it will be dropped. If it is over constrained, that means you might end up reaching the target to test, but you just found probably one possible execution path from your fuzzer to the target, but there could be many other execution paths that you might be missing. Okay. Now, to address this, we introduced these layered testing approaches. In the layered testing approach, we propose that first we will test the component that are directly connected to the fuzzer and go to the next depth or next level subsequently. So, first we will test E2T, and then which of the component after E2T is actually there. But the problem is that these components are not actually the dependency among the components, they are not well defined. They are actually left for vendors to define by themselves. So, each different implementations have different components and they have different dependencies. So, how do you find the dependencies? For to solve this challenge, we actually applied some dynamic tracing, which means that we let the RIC or non-real time RIC execute for a certain amount of time, let us say 24 hours, and we do not generate any malicious traffic or weird traffic. It is just a normal traffic. We want to see that what is the route of the input, which components the input traverses. And by doing this, we can actually see the dependency graph or dependency tree between the different components. But the issue is that we let the rig run with the normal inputs. Normal inputs are good inputs, right. So, the attacker will not generate normal inputs. The attacker is interested in generating abnormal or weird inputs. So, and weird inputs may actually take different execution paths, not just single like normal execution paths. So, dynamic tracing misses different execution paths. So, to address this challenge, we apply static program analysis. So, we first know the dependency among the components, and then we know the entry and exit point for each of these components, and find all possible execution path between the entry and exit of each component, and we do this using static analysis. So, of course, static program analysis is very challenging. There could be path explosion problem. That means there are many paths depending on the how many branch conditions are there. For example, one single component may contain 6,000 functions and over like 100K lines of code, and if you apply off the shelf static analysis, it will not work. So, for doing this, we created the program dependency graph and identified the critical path conditions and critical paths, and we ignored the non-critical paths from our consideration. And we applied different other techniques. I am not going through that, and eventually we could minimize the number of execution paths, and we find all possible important paths from entry to exit for each components. And when we know the paths, we also know the path conditions on the input, so that we can apply those conditions or constraints on the input to generate the right packet or appropriate packet that can traverse all these intermediate components and finally reach the target components. There are several other challenges. For example, the message format. Interestingly, OpenRAN, since its first release, they have changed their message formats 4 times so far. And if you change the message formats, your automated testing tool that runs into problems, because message format means that you have to also change your testing message format. So, unfortunately, there is no automated tool that can generate this ASN1 message. Mostly the messages at E2T, these are based on ASN1. So, and also there are different types of fields. So, which field you want to mutate, right? So, I mean, we do not care about the specific field to mutate, we focus on the type of the field, that ASN1 type field. And we have proposed different types of mutations that can be applied on those types of fields. The another challenge of testing OpenRAN, as if you can think of that this OpenRAN, as I said, each component running in a microservice. If there are 10 components, then 10 microservices running in parallel, right? And as soon as they receive input, they actually spawns multiple threads. And when you whenever you are testing, like you send an input, you wait for the output, and the previous execution is done, then you send the next input, right? But whenever this is the expected situation, but in testing microcontroller based this OpenRAN, you never know, like during end-to-end testing, you don't know whether the previous input actually previous execution actually stopped. Why? Because the threads were running. So, there are some ways we have confirmed that we actually developed some tool that confirms that all the threads created during the previous execution that has been stopped before sending the next input. Okay. So, this is the high level architecture of our framework called ORANalyst. The blue part, it is the first part where we run this dynamic tracing, identify the dependencies among the different nodes in RIC and non real time RIC, and from there we identify the entry and exit for each component. And then we apply the static analysis at the bottom left bottom. We identify the constraints that has to be applied on the input message. so that it can reach to the target. And then like typical fuzzer, we also have scheduler for the inputs. We also have the code coverage collection mechanisms through runtime monitors, and all different test inputs are automatically generated and then tested. Okay. So, we tested the ORAN-SC, iRelease and srRAN 1.4. These are the only two open source Open RAN implementations available so far, and our tool identified 19 critical flaws. The type of the flaws are the memory corruptions, incorrect error handlings, there are several thread issues, and we were assigned 15 CVEs. So, in general, the flaws that we have identified that exist in these message flows between the RAN and E2T interface and the rig components. So, the impact of the vulnerabilities, as I said, it can crash, it can get unauthorized memory access, and it can also, you can try to do remote code execution, take the full control of the RAN node. It depends on the programming language. If the component of RIC are written in Go programming language, which is memory safe, you can at most crash. You cannot probably do remote code execution. But if it is written in C or C++, which are memory unsafe languages, and you can do even the simple buffer flow vulnerability can lead to remote code execution attacks. That means you can actually get the high privilege. So, there is one simple example of the flaw, insufficient checks. If you look at this line, first line 264, there is an input, and that input is been stored in this variable, but before it was used, there is no check performed in the code. This is actually in ORAN-SC. Why do we care about ORAN-SC? Because many of the vendors, they are following ORAN-SC. We do not know which vendors, but this is the official implementation of Open RAN. So, if they follow this code, then of course, they are, the vendors also are running into these issues. Second issue is that mostly threading issues, the box, the red color box, that is actually taking some input and handling processing that input, and if there is an issue, they actually raise an error message, and they communicate the error message. This is the input processing thread, and this is the main thread. So, the top box is the input processing thread and bottom box is the main thread. If there is any issue in input processing in the top box, they share the error number through a channel. This is the written in Go programming language, and this channel is being shared between the main thread and the child thread. But somehow this as soon as the main thread receives that input, main thread returns. If the main thread returns, the child thread, there is nowhere that child thread can send the error message in the following inputs. So, this is the high level sort of a quick overview of the comparison with our tool and any other existing tools, and we have found more number of vulnerabilities than any other existing fuzzers. In general, whenever you create a testing framework, you actually compare your testing tool against others with 24 hours of duration. What is the coverage versus time, and what is the number of vulnerabilities versus time. So, this is the result, and ORANalyst performs significantly better than others. So, this is all about the ORANalyst, but what we need to do further to secure the Open RAN implementations. So, I discussed white box testing because we assume that we have the source code from Open RAN-SC and srRAN by the Open Networking Foundations. But how about the commercial vendors? They might not give us the source code, like they might not be interested in giving the source code to the third parties for testing. So, we are also working on black box testing and also gray box testing. Black box means that you can only provide the input output interface. I can give you the testing, I can tell you that what are the vulnerabilities, or if you give us the binaries, we can also work as a gray box testing. I showed the memory corruption vulnerabilities and operational integrity, but how about the logical vulnerabilities? For example, authentication bypass, right? I mean, if you have authentication bypass or access control policy violations, there could be different other issues. And I talked about REAK and non-real time REAK, but how about security testing of RU, DU and CU, right? And based on these rigorous testing framework, we need to propose a compiled list of conformance testing. Currently, ORAN alliance specifications are not enough. They only provide the positive testing, but what about the negative testing? And negative testing means that security testing in the presence of adversary, all right? Even we test before being deployed. Now the issue is that anything can go wrong in runtime operations, real-time operations. So we need some mechanism, for example, intrusion detection systems for open RAN systems. So to conclude, so this ORANalyst framework is the first one for testing the operational robustness for the ORAN based service-based REAK implementations. It combines dynamic testing with static program analysis, and with our tool we could identify 19 zero-days attacks, and it performs than any of the state-of-the-art testing framework. And we have open sourced this testing framework ORANalyst. Feel free to test it out. With that, I would like to conclude, and I'll be happy to take any questions.